where you don't even need to be using the same architecture across various processes. And basically, there's a lot more options and strategies for this than I can cover in this talk. One question I would ask myself if you're looking at which library to use, which tools to use, is basically, am I at the stage where I've thought through the specific model and the specific question that I'm asking, and there's nothing else clever I can do. I just want to throw GPUs and compute at this problem. In that case, for the most part, I'd suggest using some optimization like Bayesian, because that will most likely work faster, and go think about something else. But in my experience, the more interesting and challenging and rewarding work of hyperparameter tuning happens before you get to that stage where you just want to throw compute at it. And we don't really have good algorithms for it yet, which is why many of us are still in this field. So how do you do that part? And that human part of hyperparameter tuning, before you even start to tune hyperparameters, you get to decide what a hyperparameter is. And there's a distinction between the regular parameters of the network, which are learned or iteratively improved during training, and hyperparameters which are configured outside the training process and generally fixed for its duration, although sometimes they're adaptive, like learning rate. For a given network, this could include the number of training epochs, the learning rate, optimizer type, batch size, weight decay, and so on. Within the network architecture, you could think of as a hyperparameter in terms of number of layers, base architecture, connection patterns, etc. And one way to determine which hyperparameters you want to keep constant or fixed as opposed to variable, and those would be the ones that you're exploring or tuning, is to ask, how much do I know about the effect of this hyperparameter in advance? And then how much or how will this hyperparameter affect search complexity and runtime of my exploration? And a few easy ones here to determine sort of quickly, ones that we know the effect of them on hyperparameter sweeps in general. The first one is epochs, and this is the number of passes through your entire training data. And in this one, when I'm running repeated experiments, I want to set this high enough so I see definite improvement, but not so high that I'm wasting time watching a slowly converging curve. I usually try 10 or so to see if I can get away with it, as long as you see the loss decrease and start to asymptote. And seeing improvement in validation loss is especially important here to make sure you're not just memorizing the training data. Another hyperparameter that's easy to fix early is the size of your training data and how many examples you use to validate. And assuming your data set is a representative sample and your split is unbiased, generally, the larger your training data set, the better your performance. But also this means that each of your hypotheses takes a longer time to test. So overall, I try to follow the conventional wisdom of the 80% of your data goes to train, 10% goes to validation, and 10% is a held out data set, that 80-10-10 split. And as you train on the 80%, you validate on the 10% after every epoch. Like I said, this can be slow in practice. So I recommend trying to lower to 20 to 50% of that and running on that small subset, which I do anyways when I first set up my script and just make sure everything works, can help you move faster. And I try to get the runtime of one experiment down to a few minutes if I can. After each set of experiments, you can then test with a full data set, and hopefully all of the patterns you observe will hold. If adding more data doesn't actually help or hurts, you might be overfitting, and you may need to increase the percentage that you're using of your validation data set for each split. And validation data can be tricky here because the smaller sample you're taking might be too noisy. And one solution is to pick the validation set randomly each time, keeping in mind that if anything, you're solving a harder problem. And overall, the goal is to minimize the runtime of each experiment while still getting useful and representative info about your model, which leads us to what I like to call iterative sweeps. And these are repeated phases of tuning on a small subset of the data, or smaller, 20 to 50%, and then testing on the full training and validation set. In each sweep, you'll decide which hyperparameters to stay fixed, and which ones you'll be testing. And so one of your first choices is how many hyperparameters to change at a time. If you run a sweep over every possible setting of every hyperparameter, you'll need to wait days for results. But if you only change one thing at a time, you'll need to run hundreds of these iterative sweeps. And of course, this adapts to the particular problem that you're solving. And one important last thing to consider here as you're setting up for an iterative sweep is that in a perfect world, we like to see a clean and really obvious relationship between the different hyperparameters, right? And hyperparameters are not independent in reality. This is the cleanest parallel coordinates plot that I've ever made. And it's not an example from machine learning per se, but I think it does a good job explaining how these plots work. So this is a graph of economic indicators and World Happiness Survey results for 139 countries. Each country is a line, and the color of the line corresponds to the average happiness score on this survey for that country. And you can see lower scores are in purple here. I know the number line is hard to see, but it's 2.5 here and 8 at the top. Higher scores are in yellow. And then these other number lines stand for various economic indicators like biocapacity, production, imports, exports, etc. In your machine learning experiment, your final equivalent of happiness would be validation accuracy, right? And you would want that to be as high as possible, close to 100%. And then these parameters might be things like batch size, learning rate, type of network, etc. And in this really nice chart, we can see easily a clear visual trend, right? The higher a country is on any one of these indicators, overall, the higher its happiness score tends to be. And of course, I think this is a simplified picture, and there's something more complicated going on here, but I think it illustrates how we would want this parallel coordinates chart to work in a perfect world, right? Oh, every time I increase learning rate a little bit, my validation accuracy goes up, or probably vice versa, but a clean relationship like that, right? So what can we do in the much more complex reality where all of this is interconnected? A good general strategy, especially when you're pressed for time, is to start with a simple architecture, or just the best existing solution, the state of the art in whatever area you're working. After manually testing a few runs with different train and validation sizes and epochs like we talked about, maybe a few more hyperparameters, you have the setup for a first exploratory sweep. You can try a small range, like 3 to 10 hyperparameters, and sample values in a wider range. For example, for learning rate, I would try several orders of magnitude, like 0.001, 0.0001, 0.00, etc. Because the precision between 0.001 and 0.002 won't matter as much as getting the order of magnitude correct. I also wouldn't get into super fancy values at this point. Common defaults are good, and you can always focus in on the exact precision later. And learning rate and batch size, like I said, are easy to tune here because they affect the training dynamics, and getting just the order of magnitude right can be very helpful. And then I would think about picking a few more advanced candidates from architecture, such as the number and shape of filters, the layer configuration. I would also try to simplify the number of hypotheses that you test in one sweep. For example, if you're comparing 2 or more architectures, try to capture the general difference between your ideas. Let's say a regular RNN and a bidirectional RNN, or a CNN with max pooling versus average pooling, and use those as categorical variables. Because if you get too much into the details of parameterizing separately the number of filters and the number of blocks and the type of network, you again have this combinatorial explosion of experiments that you need to run, which we're trying to avoid by running these sweeps as tight, manageable iterations. And this view just shows you, again, one of those parallel coordinates charts. None of the details are a little bit tricky to see here. We'll get into a few more examples, but it's showing you the best performance of your experiment over time, and then which parameters using a decision tree tend to correlate with better performance. So once you've figured this out, how do you tell how your sweep is doing? You know, it's super tempting to watch a terminal and see the ticking outputs. And I want to encourage folks to not refresh too much. As exciting that is, we want to let the algorithm do our work for us. In this case, you know, as long as you've tested that the sweep works, then you shouldn't need to double check your results, because you're no longer conditioning a manual experiment B on the results of experiment A. You're just exploring a bunch in parallel. Usually an hour or a few hours is plenty of time if you've managed to get your runtime down to a few minutes. And with tools like weights and biases, it's easy to scale your sweep by running the same launch command on as many GPUs as you can get. And of course, periodically checking in on your sweep is sometimes useful to catch unexpected failure modes. In terms of constraining the number of runs or time, like I said, it can be hard to know when to stop and when you're done, right? I've definitely wasted more time than I'd like to admit watching sweeps, hoping there's a magical combination just around the corner that will massively improve my model. And really, I don't think there's an optimal answer to this. My heuristic is something like the pattern of results looks like it's not changing, and at worst, it's already run for, you know, twice as long as it took to get to the last maximum or best value. Then maybe it's time to try something else. And now comes a key part, which is once you're done with that sweep, to analyze the results and write down a plan, make it really concrete so that you're not reinventing the wheel and staying intentional about the process. And, you know, for me, that makes it a lot easier for my future self to understand what I was trying to do, you know, whether it's last week or, you know, a few months ago on a particular long-running project. And once you've done that, you might formulate some new hypotheses about what to explore. For example, if you're seeing that decreasing the learning rate gives you a better ultimate convergence, then try even lower values, right? You might decide that some of the hyperparameters that you've tried already give reasonably good results and change those to constants, or add new hyperparameters that you have not tried yet. And this, of course, is an iterative process. So once you repeat each sweep, you can just sort of keep going and periodically reflect on how the results are doing. In weights and biases, you can even mark some of your best runs from a sweep that you just finished to use as inspiration or a rough draft for your next sweep. So they'll be taken into account and not repeated as experiments as you keep doing this. So this kind of lets you track the space better. So now let's dive in briefly to some concrete examples, just so we have more of a sense of what the details can be like. So in this case study, I'm talking about Drought Watch. This is a satellite imagery classification problem. We have a data set of over 100,000 expertly labeled images of satellite. Each one is labeled with a 0, 1, 2, or 3 to indicate whether that location has drought. So there's no greenery, nothing for animals to eat, or 3, meaning there's a lot of vegetation, right? And these are some of the satellite images. You can see that it's pretty hard to tell at this scale, but this model actually gets to about 78%, I think, is the best one in the benchmark right now. And a benchmark is something we have on weights and biases where the data and all of the code is open and folks are collaborating on a solution. So here I ran a very quick exploratory proof of concept sweep, just 50 runs. This might be a little small, but this is a YAML file that describes basically my sweep in terms of this is the script that I'm running, the method that I'm using. So that's a grid random or Bayes in this case, because Bayes in general is going to be better for a lot of situations. And I'm maximizing validation accuracy and just exploring a few sizes for 3 layers, 3 convolutional layers, 2 fully connected layers, some dropout and learning rate. And once that runs, this is the same parallel coordinates type of plot that I talked through with economy and happiness indicators. But here, the final output is validation accuracy. So higher yellow is, more yellow is better. lower, more purple is less good. And all of my hyperparameters are these number lines here. So you can sort of trace a line as one of my experiments and say, okay, the worst performing run had a learning rate of 0.0007, had a very small second layer, medium-sized first layer, et cetera, and no dropout at all. So this is interesting. And of course, the sample size here is kind of small, and it's a little bit difficult to see the correlations, right? Maybe, a lower L1 is going to be better, maybe a lower L2 as well, definitely more dropout, right? So this can be good to visualize the space, but it's also a clear use case for this parameter importance panel, which runs a decision tree on all of your experiments and says, oh, the highest correlation is actually with dropout 2. So increasing this is likely to give better results. Or the next highest one is, actually these aren't sorted, dropout 1 is also highly correlated, but maybe less important. And this can give you a more detailed view or more precise view than this kind of visual gradient situation. Hopping quickly into a different, more exploit scenario. In this case, totally different problem. This is a project called Deep Farm that's running through weights and biases. And what we have here is PDFs of receipts, basically, that have a lot of information, such as the company that's paying for the receipt. In this case, it's political advertising on television. We have the company, the channel, the amount they paid, the contract ID, lots of information that we'd like to extract. And we could do OCR on these PDFs, but as you can imagine, the location of various pieces on the page also varies a lot. So it's actually a pretty complicated problem. And what I was trying to do is solve it with a one-dimensional CNN, running a sliding window over the text and finding high matches for things that look like, in this case, I'm trying to find the name of the company, right? So it's kind of like named entity recognition, but with a 1D CNN. I tried a bunch of manual experiments, and then eventually I ran a big sweep. You can see that there's lots of hyperparameters here, and there's some interesting correlation if you get into like the size of the sliding window, how much of the full advertiser name you're looking at as well. But the strongest correlation is definitely with the number of distractors, and that's the number of negative examples that I use per positive example to train my model. The higher the number of distractors, it looks like, I think the less it overfits is the intuitive explanation. But you'll also see that there's a bunch of gray lines in this sweep, which I didn't realize until after I sort of launched it and then came back. And this is where my process actually runs out of memory, because I'm trying to load so many negative examples per positive example that I run out of space, right? And that's why there's no validation accuracy logged here. It's just a NaN. And this is just a helpful reminder that it's not just about the hyperparameter space, it's also about the engineering constraints of the task. And interestingly, when I looked at the top performing experiments, they were pretty close, to my initial, both to my initial manual exploration based on this intuition around distractors, and there wasn't a better run found in this whole time that the sweep ran. And I think that's because of this interaction between more distractors give better results, but they're also more likely to crash the process, right? So this is maybe a reason to test more of what you launch before you set and forget a long sweep. And finally, a case where I've used a bit of both. And this is hopping to a different task. This is semantic segmentation on street scenes with cars, pedestrians, trees, buildings that you'd like to identify. And here we have some examples. This is the raw photo in the first column. The second column is the prediction of the model. And the third column is the ground truth. And you can see some comparisons here between different types of models. Under model predictions here on the far right, you can see a very detailed, prediction that's not picking up on the higher level structure. And an interesting one here is I noticed as I was trying different encoders for this, it's a UNet that uses either a ResNet variant or an AlexNet for the encoder. I was noticing that some models would identify a lot of regions in these kind of big blocks, right? So here, maybe you can see the two humans. The model predicts them as just a blob of blocks, and here's the actual prediction. I ran a sweep trying to increase the intersection over union, and you can think of the intersection over union as sort of a Venn diagram, right? For identifying exactly the pixels that belong to a human, you want that overlap of the Venn diagram between your prediction and the ground truth to be really large, and the extra bits that are wrong or on the sides that are not overlapping to be small. So that's an intuition for IOU, or intersection over union. And as I ran this sweep, I actually found more combinations of hyperparameters that correctly identified humans, because initially my models were not identifying so many humans as they're rare in the data set and don't comprise enough pixels really. And then I found it useful to look at the parameter importance relative to overall IOU versus just IOU on humans, and found that the AlexNet encoder actually is the best for human IOU because of this blocky nature, whereas overall it does less well because it's imprecise, sort of going for recall over precision. And these interdependencies are like interesting to visualize in this this parallel coordinates plot. You can see that weight decay is kind of hard to disentangle, also learning rate, but the effect is really clear here with the encoders, where all of the AlexNets actually perform lower on the average IOU, whereas the ResNet, which is like a more sophisticated and advanced model, performs much higher. So I'm getting close to time. I know that was a quick dive into some specific examples. I'm happy to answer a few more questions there. But in general, things that I found useful are having one script that you can run both as manual one-off experiments, and one that you can, the same script where you can do a hyperparameter sweep over it. Shorter runs, shorter iterative sweeps, make your feedback loop tighter. Exploring first and then exploiting later, but not too much, because you might go down a depth first tree and find a space of the model that's not actually useful. That happened with me for deep form. As I was doing all that sweeping and exploration, Google came out with a much better model, which we now want to switch to. And of course, that in your experiments, a lot of this might vary. And finally, I just have this side-by-side. That one of these panels represents actual hyperparameter tuning, and one of these represents just the same configuration with random seeds. And this is a reminder that it can be hard to tell signal from noise. The top one is actually the signal, and you can see a slight gradient in the hidden size correlated with the accuracy, but otherwise it can be hard to tell. Yeah, so that's all I have. Thank you so much for listening. I hope this helps you tune some models faster, or inspires you to explore a different type of hyperparameter search.
Great, thanks, Stacey. It's a really practical experience sharings. Can you click the Q&A? And I think we have a bunch of questions over there.
Yeah. Would you like me to just start?
Yeah, you can just from the top.
Yeah, great. So what is the software that you're using? So that's Weights and Biases, wandb.com. Hopefully you can see it linked here. You can check it out. It's a great tool for machine learning developers and practitioners. Okay, so I just answered that. Great. Giannis asks about gradient methods for computing. So how robust and trustworthy is it to use gradient methods? So I didn't really focus on that particular method here. I kind of stuck with grid, random, and Bayes. So I haven't explored gradient methods so much myself because of this difficulty, but I know there's lots of literature out there on these methods. Could you please share more insight on the visualization module used for the parallel coordinates. So that's weights and biases visualization software. Our client code is open source. You can also run weights and biases locally. Basically, what it does is it plots your hyperparameters and your output metric as a line in this space. So I don't know if that's if that answers the question, but it just draws a line connecting the hyperparameter values visually with the results, and that lets you look at a bunch of them at once and see if there's a general trend, like, oh, decreasing learning rate increases validation accuracy, or something like that. Are your projects like open source? Yeah, so if you want to look at any of my coder projects, you can go to app.wandb.ai/Stacey. I write a bunch of reports. We also have a big author program of folks doing a bunch of projects, and they share their code. And our benchmarks in particular, we're really excited for contributors to just hop in, and we have learning materials on our site as well, and lots of researchers use this. So hopefully you'll be able to find all that if you just go to wandb.com. Okay, Yanis asks, did you say that in your validation set of data you may include the training data as well? No, I did not intend to say that at all. I hope I didn't. I split my initial full set of data, right, 80, 10, 10, and then I don't ever take something out of one of those splits and put that in another split. What I was trying to say is, if I have a massive data set like 100,000 satellite images, I'm not going to take 80% of that and train on that each time, because that would be really slow. So I would instead take, I don't know, 40 or 60 or some subset of the training data split, and then take a subset of the validation data split. But I would never mix across the two of them unless you're doing a cross-validation scenario. But in a sweep, that makes less sense. Can we tune parameters for more than one metrics criteria, say happiness and wealth? That's a great question. So right now for a Bayesian sweep, you specify one metric, and you could, I think there's a different set of engineering constraints that we haven't done yet to potentially optimize across two metrics. That would be a fun extension. Right now you would have to create some combination if you wanted to represent both of their signals. There's also different ways to visualize it. For example, you could run one sweep optimizing happiness and one sweep optimizing wealth, and then plot them against each other and see if there's a region of the space that happens to optimize both. And this would be sort of a Pareto frontier, which is the visualization I'm hoping to build soon. In your case study, when you consider using OCR techniques to extract the data, how did you end up extracting the data and validating it? Yeah, so we're using off-the-shelf OCR for PDFs. I forget the name of it, but it's an existing service. And then to validate it, we can look at the original PDFs and compare. Honestly, right now there's a pretty manual process for the 2020 data set, because there's a huge crowdsourced project to do this for 2012 and 2014 for old documents. It's actually from the FCC, so it's political advertising from elections in those years. Yeah, so I think that's it. Are there other questions?
I see some questions over there. Are they already been covered, or
So I just went through all of the ones that I saw here, and I'm oh, okay, I just got one more. David asks, have you been able to benefit from the potential dependencies between the parameters? So that's a great question. I usually try to focus in on one because it feels more tangible. There's not a clear way to say like these two things need to be changed together. you know, one way in which this sometimes comes up is, for example, there's an interaction between learning rate and optimizer type, right? Or learning rate and batch size, how quickly you go through your data. So sometimes you inevitably end up changing both. I haven't seen examples where, you know, these two things need to both be set to this region, only then this effect will come up. But you could extend our visualizer to do something like that. One more. Osman says, is there any other hyperparameters methods which are better or similar to Bayesian? Yeah, so on that slide where I said there's a long tail of these, this is an active area of research, you know, both in theory and practice. There's like black box optimization services you can pay for where you don't actually know what's happening, but supposedly they might work better on certain types of problems. So this really depends on your search space and the type of problem you're solving. I recommend Bayesian just on average, but you know, if you have a really large search space, for example, or lots and lots of hyperparameters, I mean, it might be hard for a model to use Bayesian optimization to pick the best combination, right? So a lot of this is inevitably trial and error. I don't think there's like one magic solution. I know that's a little disappointing. Great, I think. Any more?
I think that's it.
Awesome. Well, thank you so much for having me.